gross. Okay. Okay, well, first, let's go ahead and talk about what we did last Friday. And I know we only have like 30 minutes, 25 minutes left, but we'll do this fast. Okay, so what we talked about last Friday is basically we gave everyone an idea of how to 3D model. And we posted some pictures you guys can see here. Scott took this real cool picture. It's like one of those like 360-degree pictures of the lab, which is kind of cool. It was kind of cool that he had that on him. But yeah, so we got to learn how to 3D model a bit. The basic idea was, before I get to that, if you guys haven't seen it on the general chat, you guys can see the new motor that came in. So we got to play around with the new motor since it arrived at the lab and it was still unopened. So we got to see the new motor. This is everyone at the lab. We had a pretty good time figuring out how to 3D model. This is Urban with the new motor. It is absolutely massive. Yeah, so this is a size comparison of the old motor here, the Loki M3000, and the new motor, the Cicerone, what was it? What? Does anybody know? 2600 or something like that? But anyway, we went from 3 inches to 4-inch diameter, and from like, how long was this? Like 100 and no, what was it? Anyway, it's not important right now. But yeah, we got to play around with the new motor. It is absolutely massive compared to the airframe, and it's gonna make a really loud sound. So I'm excited for that. Okay, so let's get into it. So as we saw Friday, we have a 3D model. Once we have this 3D model, and this is kind of continuing on the little video presentation we had last Monday, which I'm going to post both of them after this. But once you have your 3D model, this is a little coin that says propulsion on both sides. I know on the back side it's kind of backwards, but it adds to the charm. Once we have our 3D model, we can go ahead and put it into our software that'll allow us to 3D print it. So you see here, whenever we save this, it is saved as an IPT on the lower corner, coin.ipt. That basically stands for inventor part. I don't know what the T stands for, but it's an inventor part. From here, we can do one of two things. Either we do file, export it or save as, and save it as a different file type. So if you do save as, save copy as, your file name, and then on here, you can select what kind of file types you want. And usually the file types we're going to be using for 3D modeling is going to be STL. So you could save it there, but in order to keep the dimensions like proper, because every single one of these shapes has a specific dimension to it, in order to keep your dimensions identical to the model, you have to modify some of the settings on your conversion. But in order to make things a lot easier for us, we open up Cura, which is our 3D modeling, 3D slicing software, which basically takes a 3D model we have made and slices it so that it can be 3D printable. Now, Cura, I use Cura mainly because it's very easy to use. It's very popular. It works well with the printer I have, which is the Ender 3. But the main reason I use Cura is because on the marketplace, you can see here, there are integrations for specific software. So you can have many different plugins that will allow you to automatically input an inventor file into Cura, and it'll automatically convert it for you. So you don't have to worry about converting it or worrying about units. It'll just give you exactly what you made. There's also Siemens NX, which some of the team uses because we are sponsored by them. and also a bunch of other stuff. There's Blender, there's SolidWorks, there's FreeCAD. So there's many different plugins that you can use to integrate your files and convert them into STL files. Okay, so now here we have our little 3D model, which was what we made here. This little coin is what we made. And now we have it input into our 3D slicing software. From here, you have all these different options on the left-hand side that'll allow you to scale it. So if you want to make it a little bit bigger, we can scale it. We can rotate it in many different angles. We can, what is this? Oh, mirror. Okay, cool. Mirror, lay it flat, but let's say we just like how it is here. On this right-hand side, you have all of your different settings for your printer, and I kind of opened up the majority of the ones that are important. Most of the other settings are to make some fine details or adjustments to the 3D printer itself, or how it reacts or how it acts to the model. But I think these are your basic important ones. So of course you have your layer height. If you see a 3D printer, whenever it is actually printing, it will do it layer by layer. And when it does it layer by layer, it'll look something like this. So you can see the little nozzle at the, oh, hold on, not that one. It'll look something like this. So you can see at the very first layer, the printer nozzle will start, what do you say, laying down or distributing like the melted plastic on the first layer. And this I love this little animation because it keeps me from having to like show you on my actual 3D printer, but you kind of get the idea of how a 3D printer works. And if you can see closely, you can see that every single individual line is being laid out. Oh, we got a message. Oh, okay. So every single layer line is being laid out one at a time. And if we speed it up, we can see how the first layer is going to look like and how it starts building the model. So you can see here, the blue is just a support structure and the red is actually the model itself. We can go up a layer and see how the next layer is going to look like, and so on and so forth. And if we do this, you can see how the 3D printer slowly starts building the model layer by layer. Now, each one of these layers have a specific depth, like height to them. So the smaller you make these layers, the more detail your 3D print's gonna have. If you can see here, I have it set to dynamic quality, but if we set it to low quality and slice it again, come on, we can see that for one, it prints a little bit faster, and also there's less detail. There's less lines. Each line is thicker here. And if we make it to really, really fine detail at 0.12 millimeters, which is fairly detailed for a filament printer, you can see how many layer lines there are now. And you can see that doubles the amount of time that it takes to print. From here, that's your layer height or your quality. I actually have this really cool plugin that allows you to basically gives you a description of each individual setting. Here's your infill. Your infill is basically what is going to fill the inside, because whenever you make a 3D model, whenever you go to print it, it acts as a shell. So the entire interior is empty. And then it does it that way to save you time on printing. However, you do have to fill in the inside in order to add some form of support structure to the inside. So here are all the different types of infills that you can print with, and each pattern will have its pros and cons to each pattern. So for example, this one here prints very quickly, but it has really good strength vertically, but horizontally is very weak. Or this one here, what is it? Cubic, a lot of people use because these triangles kind of interlock across each other. It creates a very strong structure on all sides. But anyway, so that's your infill. In this case, we have 40% set to lightning. It's a new type of infill, but we'll do a cubic so it's easier for us to see. lightning is a little, there's the math behind lightning is a little complex. But anyway, so you can see here the interior, which is this orange, the infill is at 40%. And if we reduce it, let's say that's too much material being filled into this empty volume. We'll do it to 10%. And we can see that it changes not only the time, so it reduces an hour of the print time, but also reduces the amount of material we needed. So before we needed like 20 something grams, now it only needs like 12. Okay, and then of course support. If you have really sharp angles, your 3D printer is going to have a really tough time printing these sharp angles, mainly because your printer is not able to print in midair because there's nothing to hold up the material. So you can see that support structure being shown off here. So you can see here between this layer and this layer, this entire yellow section is being printed in midair. So in order to support this from drooping down, because it's melted plastic, you have to support it with this darker blue support structure. And in this case, we just have some normal support structure. There's different types, but we just have a normal support structure. And we have our angle. So you can see here an example of different, what choosing a different angle does. This is a higher angle, so it only supports higher overhang angles. This is a lower angle, so you can support more of your overhang. In this case, if you were to print this here without any support, it'll just completely fail on you and it'll come out really bad because you're printing in midair. So it'll droop, it'll look bad. And then lastly is this build plate adhesion. It just allows you to build it, what's it called? Stick it to the main building surface. But once you slice it, all right, come on. Okay, but once you slice it, you get an idea of what you're looking for. You can get an idea of what it's going to look like. You print it, and it should come out on your 3D printer. And if you guys are interested on the Discord, I believe there are a bunch of different examples on different sub teams that have 3D printed stuff in the lab. For example, this boat tail. Where did it go? I think it was down. I think it was just this one. But anyway, you can see this boat tail. This piece has been 3D printed, and they're using it as to cast this fiberglass mold. So you can see how useful 3D printing is for us in the lab. And this is the final mold negative, which you're going to be using to create a boat tail that is not 3D printed. So really, really useful. Okay, so that's enough for 3D printing. We'll get rid of all this stuff. And now we got to talk about propellants. Okay, so the reason we need to talk about propellants right now, and you guys are welcome to join in the conversation if you have any questions, or Adrian, if we want to talk about what we're planning on doing this coming Friday. We have to talk about propellants because we need to start making fuel in the lab to prepare the team for basically the next, 2 years. So we are, I know it's kind of like a pro and con of being like the first people to start doing this at the Rocket team, because a lot of the people who start off doing it don't really see the final, basically don't see the final product of what all their work is going to accomplish. And the reason is because a lot of us are going to graduate before some of this stuff gets done. Okay. To start off, we need to understand that fuels are very dangerous, no matter what we're making, even if we're making like some real inexpensive sugar fuel. And if you guys are interested, what we're planning on making is sugar and potassium nitrate. It's already on my history. Okay. Oh, great. Smoke bomb. Rocket fuel. So you can see here, this is basically what we're going to start off making. We're going to start off making sugar rocket motors because they are very, very inexpensive. It's basically just fertilizer and sugar. Very cheap, but it'll give us all of the fundamentals that we need in order to start making bigger motors out of the much more powerful propellants. So you can see here, kind of like the cross-sectional area of what the motor is going to look like. When working with these solid motors, because they're very simple, we really don't have to worry too much about our nozzle shape or our angles on our nozzle or our ratio between the thickness and the length. There is a lot of math and science that goes involved in that is involved in making rocket motors, and I think I had kind of like a short presentation about that last semester. But because our sugar motors are very easy to make, and here's one of the tutorials that basically tells you how to do it. Now, on many of them, for example, on this one, all they do is mix it, but there are a lot of them where they actually heat it up and create a kind of like caramelized propellant that they can shape and mold. So we will get some experience with both, just mixing it and keeping it in powdered form, or melting it and creating basically fuel grains. So this is what we're going to start off with, and it is a very simple ratio. Where was right here? So it's a very simple ratio. You can see here they're using sorbitol, which is a different type of sugar. Red iron oxide, this is one of their modifiers. The red iron oxide could either be for performance or aesthetics. So depending on how much you put. In this case, I'm thinking they're just trying to make some sparks or some color changes to the propellant, because it's a little pinch and it's not enough to modify the performance of the sugar rocket fuel. So you can see here 65% potassium nitrate, 35% sugar, and you basically just mix it in together, create your solid fuel, shape it. So there he is mixing in the two chemicals. This is the potassium nitrate being added to the sugar. And then he starts off with a cardboard tube or a motor liner in this case. And then he just fills it in with clay to block off the edges and the fuel. And then he drills through it to create that inner core. So that's the super basic understanding of what we're going to be making. But before we can do this, we have to go through some very important stuff. We do have to talk about the safety of what we're going to be doing. Even if it is a simple homemade sugar rocket propellant, it is still a propellant at the end of the day. It is still an extremely powerful oxidizer and fuel. And because of that, if it were to light up inside the lab, it has a high probability of causing a fire. So we have to be very careful when making it. We have to talk to the chemistry department, the fire department, to make sure everyone's on board and everyone understands what we're doing. And the reason we have to do all of this, all of the behind the scenes, all of the, what's the word I'm looking for? Hold on. Permissions, all the permissions we need, is because I believe it was, I wasn't sure if it was like Massachusetts or Michigan, but one of the university teams got completely disbanded. And they got completely disbanded after not reporting or applying for the correct permissions to test their liquid rocket engine prototype. And whenever they went to test it, it blew up the container that they were holding it in, made a really loud bang. A lot of people got, like in the neighborhood, were freaking out because they've just heard an explosion, and they got disbanded for not getting the right permission. So we have to be careful with that. Making chemicals and making motors in the lab can have big consequences, but if we do it right, we wouldn't have any problem. And we're doing all of these. I think I can stop sharing my screen. I really don't have anything else to show you guys here. This is just a list of different solid propellants, liquid propellants. In our case, the only thing we're going to be using is, where is it? Nope, that's not that one. Ammonium perchlorate, potassium nitrate. So you can see here, even on the wiki on rocket propellants, we're going to be working with these chemicals. Ammonium perchlorate for our for the fuel that we're going to be using on making the big motors, but potassium nitrate for the simple sugar motors. So you can see here, burn rate modifiers, iron oxide, copper oxide. So that's what that little pinch of iron oxide was here, red iron oxide. And solid propellants are usually very simple. The only thing they need is a fuel such as, where is it? No, this doesn't have the percentages, but a fuel such as sugar or in ammonium perchlorate's case, it'll be aluminum. Aluminum is the actual fuel. And then these are oxidizers. Ammonium perchlorate is a really good oxidizer, as you can tell. And potassium nitrate is also a very good oxidizer because it breaks down very quickly. Okay. So I guess we can stop sharing my screen. All right, and now we can talk. Basically, what I think we should do is Adrian and I, and we only have 5 minutes. So Adrian and I are going to talk to the chemistry department, talk to the team, the project manager, and the lead engineer, which is Irvin and Gus, in order to get an understanding and idea of exactly what we need to do before we can actually start making rockets in the lab. If it doesn't get done this week, I still think we can have some stuff to do on this coming Friday. But if we are able to do it within the week, then we can definitely start the process of making rockets, like little homemade rockets, in the lab on Friday. So I recommend that everyone show up for that, because it is going to be kind of cool what we're going to be making. And because they're very small, we don't need any heavy permissions from the school to test it out on an empty field. So I'm thinking we just launch a couple really small ones into a brick on the floor and see how they fly. Or not fly, see how they perform, because they're going to be pointed down because you don't want to shoot them. Okay, so that's what we got looking forward to us. We have to, this will allow us to create, what's the thing I'm looking for? This will allow us to create a safety procedure guideline for our upcoming, I mean, honestly, for the rest of our school year. Let me share my screen one more time. So you can see here, this document here is kind of an idea of what I'm interested in making for the solid propellant and for the hybrid rocket motor. We have to input all of this information. And of course, this has to be detailed. It can't just be, like titles and subtitles like it is here. But every single one of these things has to be detailed, because we have to write everything down. If we don't, all of the engineers at Spaceport will get really, really upset with us if we're not writing this stuff down. So, scope of work, design, fuel types, standard operating procedures, how we're going to test them and use it. So basically this exact thing, but this is for the hybrid motor, this exact thing, but for solid motors. Of course, duties in manufacturing, who's going to be doing what's going to be being done, and then mainly safety. We have to make sure everyone's safe because we don't want anybody getting hurt in the rocket team. And nobody has been hurt yet, so that's perfect. That's a good reputation we want to have. But yeah, that's basically all I have for you guys. We're going to be making those sugar motors. So maybe sometime this week, or maybe even Friday, we can go buy this stuff here, which should be very inexpensive and easy to come by. We'll go get some, what is it? Some of this stuff, which is also very cheap. And we can start making fuel in the lab. And from there, we'll just make bigger ones and bigger ones. And then once we're comfortable enough, we can start making ammonium perchlorate propellants, or as it's normally called, APCP. Awesome. Okay, that is all I have, and I have a minute and a half left on the meeting. So you guys are welcome to ask or say anything y'all are interested in.
So for the ammonium perchlorate, we're doing that after the sugar, right? The sugar
Yes.
rockets.
Yeah,
Okay.
because it is a lot more expensive. And we need to fly Zenith before we can actually make the motor for Oberon, because there's already a motor for Oberon.
Is ammonium perchlorate just straight up solid propellant?
Yes, ammonium perchlorate
Okay.
is straight up solid propellant. And just as a side
Okay.
note, on hybrid motors, the majority of the people use the exact composition of ammonium perchlorate, but they take out the aluminum and the ammonium perchlorate and just have the binder, which is like the resin, to run their liquid hybrid motors. But we're going to be using paraffin wax. But all right, we got less than 1 minute, so I think we'll leave it at that.
Yep.
All right, thank you guys.
Thank you.